Good afternoon, everybody. I'm Brock Hedegaard from the University of Minnesota, Duluth. I will be presenting on time and temperature-dependent deflection monitoring of the I-35W St. Anthony Falls Bridge. This is the new 35W, or new-ish at this point. It was built in 2008. We'll talk a little bit about its history. So this is work in collaboration with Dr. Lauren Linderman from the University of Minnesota Twin Cities, and two students there, Riley Brown and Rebecca McCoy, helped with this particular project. So without further ado, just a quick overview of the bridge and some of the instrumentation that we had on this particular structure. So the I-35W St. Anthony Falls Bridge has been monitored since its opening in September of 2008. So of course this is the post-tension segmental concrete bridge that replaced the steel one that collapsed in 2007. Built at a very, very fast timeline, under 1 year actually, from collapse of the previous bridge to opening of the new one. So it was a very fast time frame. This bridge contains over 500 sensor channels, some fewer sensors because some of the sensors themselves will have multiple channels that, say, collect temperature and strain at the same time, to investigate the behavior. So our strain gauges, we have a variety of vibrating wire strain gauges, thermistors, accelerometers, linear potentiometers at the expansion joints to measure displacement there, and fiber optic strain sensors as well. So this data set is one, uniquely large, and two, the fact that we've collected this since the beginning of the since the bridge was constructed, gives us a great opportunity to investigate structural characteristics and how they can change over time, and observe temperature and time-dependent behaviors. And we saw a great overview of this with the first presentation, and as Todd actually kind of hit it, I'm a Montana native, so I was kind of excited about that anyway. Less excited that their bridges are falling apart, but excited that they get a little bit of showtime there. So we'll see some kind of similar things actually in Minnesota. We have northern climates are going to have very large thermal gradients and things like that, so we'll see that again here. So just an overview of the instrumentation that we have in this particular bridge. Here's just an aerial shot of the structure. The yellow triangles here represent the linear potentiometers measuring expansion joint displacements, so that's a horizontal displacement. Accelerometers are placed at any of these purple circles. We use those for modal analysis. I'm not going to talk about them a lot here, just a little bit. And then we have a variety of vibrating wire strain gauges at all of these blue squares. The star right at the middle was our main thermistor array. So they're located throughout the deck. There's about 6 thermistors to the top deck of the bridge. And the vibrating wire strain gauges also have an integrated thermistor with them, so we're getting temperature all over this particular structure. The fiber optic are long gauge sensors here. We won't talk too much about them. They're really durable. They're really great. In fact, in terms of the robustness of the sensors, we've been consistently impressed. I think even after now it's been about 15 years, we have about 90% survival rate of the sensors, and most of those that went out in construction due to things happening to them in construction, cables getting cast into concrete or stepped on or other things like that. So in terms of survivability, it's actually been really quite great, other than a couple electrical issues with the linear potentiometers. So you'll see like gaps in the data where stuff happens there. But so one of the challenges of long-term monitoring is behavior of in-service bridges are dependent on a lot of different phenomena that are happening out there in the real world. And degradation of a structure is not going to be generally sudden. It's going to be happening slowly over time. And it can be masked by your normal behavior. So when I say what we would like to see, we don't really want to see degradation, but it's inevitable. So we'll see it. It's like, hey, here's some sensor data. It's looking great. We got some white noise or something like that. And oh, it's moving. We got some displacement. We have some strain. Something bad happened. The real world doesn't work like that. It just, in general, reality is going to be data that looks like this or similar to the strain data that we saw earlier. We have extreme seasonal variations, daily variations in our strains. There is a time-dependent component to this due to creep and shrinkage. The green line here is the temperature, I think at midspan. So one of these, I believe the red one is like a top strain gauge. The blue one is a bottom strain gauge, but we can see lots of effects going into these. And if you told me, and I'll also mention there was a outage right there when we had some kind of power surge, I think, and then we had to replace some electrical components, but it otherwise worked okay. So sometimes you'll also be missing data. It's not a full continuous series. But the point is that this is much more challenging problem. We can't just say, oh, it's like, oh, well, when the strain exceeds X, then you got a problem. So next, before I talk about like more about the data and what we're learning from it and what we have learned from it, why are we specifically looking at temperature and time? Well, first of all, we really need to know those normal operational conditions of the bridge. That's going to be key to extracting any anomalies that we see in that. So if I don't know what this is supposed to look like, there's really no hope of me trying to find something unusual in it. Furthermore, this is the largest signal that we get on the bridge, and so having a good signal is always important. The ambient thermal loading on these things is ridiculously huge compared to the traffic loading, which you basically can't see at all in the data. And long-term creep and shrinkage can lead to a variety of issues, either at the bearings, expansion joints, post-tension losses, things like that. And so it's a useful thing to track over time. Plus, I'm very familiar with creep and shrinkage, so it's kind of my baby in some ways. But if you've looked at the different time-dependent models for doing this comparison, they're all different, and they're probably all wrong. And I say that as a person who's developed one of these, so that's fine. Like, they're probably all wrong. And if you don't have like actual data of the structure to see what is happening, it can be very difficult you can make a prediction. It's like, okay, that's nice. I want the data, get some material data, get some field data, and see actually what's happening, how these things move. What I want to talk about first is some of the interactions that we see in some of the sensors that we have in the structure, and particularly how they interact with temperature, because again, that's sort of our driving effect for most of our, what you call loading here. So first of all, if we think about modes of vibration, so this would be natural frequencies, mode shapes, things like that. Oftentimes we'll just assume, hey, natural frequencies are constant, it's great, let's see, maybe we can see if they change with time, and if there's a change in the natural frequency, you might have a problem. Again, not that simple. They change dramatically actually just with temperature, and you can actually see sometimes there's a bifurcation when you have a difference of below freezing versus above freezing. So on the y-axis here, this would be the frequency that we've measured using our accelerometers. This would be the first natural frequency associated with the primary bending mode of this bridge. And of course it does vary, and there's a decent amount of scatter, but it is also a rather unique fit where you have a different line above freezing versus below freezing. Plus it can be different when you're looking at different kinds of modes. So if we look at this is the first torsional mode. We can tell that because we have accelerometers in both boxes of this. So when they're out of phase, then we know that's a torsional mode. And that doesn't behave in the same temperature way as a flexural mode. So it actually has a different sort of shape here, a rather flat line, and then a different curve once you're above freezing. So why exactly this happens, we're not entirely sure. I mean, some of it is going to be due to just slightly, possibly different compliance and stiffness of the concrete and materials in different temperatures. But then there's also going to be effects of the boundary conditions, what exactly is happening on those bearing pads and bearing plates and things like that when you're above and below freezing can be a pretty complex topic. So we haven't quite totally figured out what that is, but we see it. It happens. Next, thermal expansion. Oftentimes we'll assume that coefficient of thermal expansion is a constant, and it's pretty close to 1. But what we ended up doing is we'd sample just like individual months throughout the history of the bridge, and we would look at what is the coefficient of thermal expansion for that month versus another month versus another month, and so on, and then plot that against the average temperature that we observed during that month. So down here, this would be during the winter. Average temperature slightly below freezing in 20 degrees Fahrenheit, and then in the summer up around 80 degrees Fahrenheit here. And it does have a markedly linear trend. There's a number of reasons that have been postulated for why this could be. For example, when we have higher temperature, the particles could be further apart. So your pore network is effectively could be changing with different different temperatures, and that meniscus is going to slightly change the internal relative humidity of your concrete. So that could potentially have effects, as we saw before, in changing strains and things like that. So there's going to be some interaction there So coefficient of thermal expansion is not quite as cut and dry and simple as we always wish. We also have very high thermal gradients in Minnesota. A lot of northern states are running into this issue. The assumption is that a temperature difference through the top deck is probably going to vary according to AASHTO LRFD design gradient, which is plotted here in red, and we can immediately see that the black dots here are some of the peak gradients that we saw in throughout the bridge deck, and it does not fit the AASHTO gradient at all. It fits closer to a 6-order curve here. This Priestley curve is what's used in New Zealand design, and that's actually much closer. But key thing to take away here is that this shape of your gradient curve and the higher temperatures that you observe does cause a lot more stress in your bridge deck than a design gradient like this. So it's actually possibly unconservative to use this AASHTO design gradient, depending on your region and the magnitudes. But for this particular bridge, we would have to increase that gradient to actually get the proper thermal stresses that are occurring in this bridge. So that was a little bit nerve-wracking. If we compare it, it doesn't happen all the time. So again, these are the peaks. But it happens pretty consistently. So the plots here on the right show how many days, and I believe this is was this a month or a quarter basis? I think this is on a quarterly basis. Yeah, on a quarterly basis. How many days would exceed that positive gradient? And so per quarter, 10 to 15 days would regularly exceed the design gradient. And so it's not like, oh, this happened once or twice. This happened over 100 times throughout the service life of this bridge so far, and it's going to happen a lot more continuing going on. Negative gradients is down here. That would be if the top bridge deck is colder than the web, for example, and we exceed that similarly, so both in positive and negative gradients. Negative gradients usually aren't as big, but positive gradients are usually a little bit more important to look at. But anyway, there's very large temperature differences in this bridge. Finally, our last interaction with temperature is in terms of the creep and shrinkage that we see. So our assumption, creep and shrinkage strains progress smoothly with time. And the observation doesn't really happen. So if oh, that's really hard to see. I apologize. I didn't know it would be that tough. If you're sitting very close to the front, you can see I tried to shade this blue for a winter and yellow for a summer, and then blue for a winter and yellow for a summer. Anyway, in winters, here, and this is only plotted for a couple of years just so we can see it. It's a little bit easier to see. Creep and shrinkage practically stop, and then they accelerate and sort of catch back up in the summer. So you get this sort of stair-steppy behavior. And it's very pronounced in the first couple of years, which is why I've only plotted the first couple of years, because obviously creep and shrinkage are going to slow down after that, so it's a little bit harder to see. The red line is the bridge temperature, so that can also maybe give you a little pointer. So low temperature means the creep and shrinkage basically stop, and then high temperature, that sort of accelerates back up. So what do we do with all this, and what are we going to do with this data? That's always sort of the important takeaway message from any bridge that's monitored. I always like to tell my students and others and anybody that'll listen basically that your monitoring system is just as much an engineered system as your bridge itself. Like, you have to think through, what instrumentation am I using, what am I collecting, how am I collecting it, how am I going to process the data, what am I going to do with that data, and what problems am I solving? We're not just going to slap a sensor on a bridge and say, cool, I looked at it for 10 years, and it was neat. Like, we're trying to learn from this and diagnose something of value. So in terms of what's the value that we're going to get out of this data, what I wanted to do is try to remove a lot of those temperature effects to get a nice smooth curve, trying to predict a time-dependent deflections or strains, to track how if that's going with post-tensioning losses or movement of the bearings and such like that. So to start off, we'll start off with a linear regression. Our measure data is y here, and then we have an axial elongation. You'll notice there's two terms there, which is representing the coefficient of thermal expansion, which is not necessarily constant with temperature. There's going to be a thermal gradient term, and it's a modeled time-dependent behavior. I'm trying to extract that, but I got to make some assumption so that the regression is going to work. So we'll assume something there. It doesn't matter what you assume as long as it's close. So you can use a variety of different time-dependent models, and it works pretty well. And once I find the coefficients for my temperature behavior, I can subtract that out, and I'm left with what I'll call a measured time-dependent behavior. You'll notice that this term got axed effectively, and it becomes this measurement. So here's my data once again, and I'm subtracting off the temperature-related components. I'm left with the measured time, plus the delta, which is some residual that I don't know where it comes from, basically, so it can't go away. That's right over here as well. All right, so what does it look like? Again, it's got the stair-steppy behavior. It's a little harder to see now that I'm plotting it out for about 10 years here. The gray line is the expansion joint at the end of span 3. That's a 3-span bridge. And then the black line is the expansion joint at the end of span 1. And so this red line is predicting basically the overall shortening in this case. I plotted it positive just so it's easier to see, but overall shortening of the bridge from span 1 to span 3, because that's the distance between my two expansion joints there. So to correct this and make it a little bit more smooth, we'll apply an Arrhenius equation to convert this to what we call an equivalent time. Equivalent time is effectively, well, if this bridge were instead held constant at a reference temperature, and we'll just say room temperature because that's convenient, 68 degrees Fahrenheit or 20 degrees Celsius, what would this look like? And it looks much smoother in general, especially in that early age right here. It looks much more like a typical sort of creep and shrinkage time-dependent curve that we can see with those stair-steppy behavior knocked out. So what's the benefit of this? So first of all, we can start looking at anomaly detection. So deviations are going to be much easier for me to detect, just from a time-dependent behavior rather than from this like crazy thing that's going all over the place with all possible effects going on in there. It's a versatile technique. It works for the strain data and for displacement data and a variety of other things that are going to basically move with your structure. And now it's going to open up our possibilities for FEM comparison, because if I'm oftentimes will model our FEM model at just a constant temperature, I'm like, I don't really want to vary the temperature on the model, it's hard. And so I'll just do it at a constant temperature, and I've accounted for all possible, at least I think, all possible temperature effects in there, both in the creep and shrinkage rates, and also in creep and shrinkage strains and thermal expansion and things like that. So now I can just do a straight up comparison if I run a time-dependent model and see how it works, how they compare. So that's what we did. In terms of the modeling, it's a full 3D FEM model, also built in Abacus. Hey, that's quite handy. It includes aging, so the material properties change with time, creep, shrinkage, relaxation of the strands. We ran it for 150 adjusted age years. By that I mean the simulation was 150 years long, and the temperature was remained at a constant room temperature. We looked at 6 different creep and shrinkage models, 4 sort of code-based asymptotic creep models, and 2 more logarithmic models, B3 and GL2000. Asymptotic just means it ends at some point. And then the logarithmic models will go off infinitely. It still slows down with time, but they keep creeping basically forever. Technically, if you want to be really pedantic, GL2000 is not officially a logarithmic, but it takes, I think, about 1,000 years to reach the asymptotic limit, so I was like, close enough. So that's what we roll with. Anyway, so if we compare our FEM predictions with some of the strains that we saw right here, zoomed in on a linear time scale or zoomed out on this log time scale, we can see that 1, all the models are very different, and 2, it looks like the CEB 1990 model is looking pretty good, but that's, I think, more just dumb luck than anything else. You try a different bridge and you're going to get a different model that works. So I wouldn't put too much stock in this. But it is interesting to see the variation in different predictions that you can get, where if you're using the classic ACI 209 model, for example, creep and shrinkage are theoretically already done at this point, and the data says, nope, it's still going pretty strongly, actually. If we zoom in on the log time thing, we can see, yeah, it is definitely still going even after about 15 years. Still creeping, still shrinking. It looks like it's curving up. The shape of the curve actually looks much more closer to the logarithmic functions. It just happens to be that the logarithmic functions have a much larger amount of creep. But shape-wise, it's actually much closer to those two than some of the models that have ended their creep and shrinkage rather early. And there's theoretical reasons which we won't get into right now, but let's see. This is just more comparisons. at different locations. I think we kind of get the idea, but the reason I bring this up is even if you're looking at different locations throughout the structure, it's like, oh, maybe a different model works here. Well, there's a lot of complex interactions depending on if you're looking at, say, negative moment regions here at the pier, or positive moment regions, or even in different spans. So it gets quite complex in where you're looking. So that's why I say I don't want to put too much stock into say this model's right, this model's wrong, but just a scatter of the different predictions that you can see and how, and general trends of the data that we're also observing here. Again, just a few more looking at total shortening. Again, if we look in log time with this plot right here, it just keeps going. So it hasn't really seen an end yet. And so it's looking closer to these models that just keep going, much less like classic AASHTO model. That's the 2010 AASHTO model, and then the ACI 209 previous model there. So what do we do with this information? I'll kind of go through this quickly because I think time is running a little bit short. But so we can try to implement some anomaly detection schemes with this data. So there's two different ones that we delivered to MnDOT. So the first one we call the short-term anomaly detection. It relies on Bayesian regression, which is the idea where we have some prior distribution, which is basically our initial model run, which is the mean here. And then some uncertainty associated with that, which is quite large because uncertainty in creep and shrinkage predictions is quite large. And then we'll say, well, given an initial prediction and the uncertainty in that, can I update that using my data? And the answer is yes. That results in a posterior distribution, which gives you a much tighter fit. So using that data and this model sort of in conjunction to try to get credible bounds here. So the credible bounds, the blue lines here, mean prediction. And then using this as a way of saying you may have an issue in your bridge if this is outside of your credible bounds. It does depend, obviously, on what type of creep and shrinkage model you're using. And so that is definitely one trick and one consideration when you're going into this. We assumed that the time-dependent model curve itself was a deterministic choice, basically. That may or may not be true, but use some care when doing this sort of extrapolation because it is model dependent. And it can at least see simulated problems. We didn't have any actual problems in the bridge, which was nice. But here we simulated a problem of bearing lockup by just changing its thermal response for about 10 days there. And it clearly, this is just a zoom in of the last like 100 days or so. It clearly like shoots off when you change that thermal response in that region. So we're pretty happy with that. In terms of long term, it was a little bit harder to look at the total creep and the total shrinkage. So instead what we wanted to look at was the creep and shrinkage displacement rates and strain rates. So here on the y-axis, it's we call it a slope, but it's really millimeters per day in this case because this is how much the bridge is shortening per day. So how many millimeters is that bridge shortening per day? And we're looking at the two different expansion joints here. You can see it's not always a nice smooth curve, but we can do a similar sort of Bayesian regression here and seeing those credible bounds to see, well, if your displacement rate changes rather extremely, then you might have some issue where this thing is moving a lot faster than you were expecting, or perhaps even in the wrong direction. All right, so to summarize, temperature effects in general is temperature is doing much more than just an axial thermal expansion on your bridge. Yeah, that's what the expansion joints are there for. It's helping you with that. But there's many complex interactions with a lot of other phenomena that are present in your structure. Feature extraction, where we extracted the time-dependent deformation from the raw data, is really helping us observe those trends and the possibility of finding an anomaly rather than just looking at the raw data on its own. And we applied Bayesian regression, which is a nice tool. I really am a big fan of it in terms of understanding that uncertainty and that we have some credible bounds that we can say, it's like, hey, we can make a decision based off of it. If we're outside these bounds, we can possibly take some remediation or some other action and warn the DOT that something crazy is going on with the bridge. So with that, I'd like to thank the sponsor, which is Minnesota Department of Transportation. We just wrapped up this project in 2020 with them, and we always hope for more contracts so that we can continue looking at their data, but it's still being collected. But yeah, that's all I have, so thank you very much. All right.
we have time for a quick question? Just one.
Yes.
Noise data collected. I was just wondering, how can you filter observations that are potentially due to the material aspect, like temperature dependency and so on, versus potential structural aspects like imperfections, cracking, localized damage, non-symmetry? How can you really filter those?
Not easily, especially when, effectively in this case, we're really just looking at the data from the entire structure overall. So is there going to be a mixture of those kind of effects throughout the bridge? Yes. Could you get it possibly by looking at differences in different locations of the structure where it's behaving in different ways and say, well, okay, perhaps we'll assume, which is not entirely correct, that the material is constant along the whole structure, like so then we'll hold material constant and see if you alter the structure in some way, what that does to your data, what that does to the response, and then you could look at a different case. So let's say now I'll assume my structure is in perfect condition. What if I start varying the material properties? Starting to try to explore that. That's not something we specifically looked into, but it's a really good idea, and it gets part to the point where, you know, here we're looking at the macroscopic view. You have bridge data, and the bridge's materials arranged in the structure. Like, how do I separate the two? I don't know the answer to that, but I think there's maybe ways that we could think about it and approach it.
Because you're running 3D model, so that's the way to run.
Yeah, so there's definitely ways where you can look at variations of different types of, you can vary the structure, you can vary the materials in some way and at least look at it. So I think that's actually a good thing to think about, yeah. It's not something that we did, though.
Okay, if you have a comment.
Oh, yes, Hani.
That's very good work. I wonder if it's a good way to validate creep and shrinkage model using field data, because what you're collecting is the total strain. And I wonder, how do you separate the creep and shrinkage with thermal if you are collecting total strain?
So creep and shrinkage are not specifically separable in this case. So yes, and that's another reason why I don't want to make sort of sweeping conclusions on like one model versus another, because
that bridge they already did. Somebody else from the Navy that they used this bridge to validate the use of data. And I wonder if you have an idea, how did they separate the thermal at least from the creep and shrinkage?
I don't know. That's a very big task. I mean, separating thermal from creep and shrinkage is one thing, because we do have the temperature records of the structure, so that can be feasibly done. Separating out the creep from the shrinkage is an entirely different story. We don't have any sensors that tell us stress, right? There's no stress sensor in the bridge that tells us, oh, well, you're under this particular stress. We have lots of strain sensors, and we can use that to estimate a stress, but it's very difficult to separate those two. You could get an approximation if you knew your stress, and then the stress history of the structure. That's probably about as good as you're going to get. It's a very complex problem, though.
Oh, you can't do it here.
Okay.
There's no.
Well, I got to catch a flight, so perhaps not right now.
I think you can copy in this.